So this video is going to be about finding volumes of solid figures when you rotate a line about an axis. So let's say we rotate this axis or we spin this axis. This line will trace out a solid figure like a horn or something. Maybe you could imagine this axis turning, and that would make a figure that looks something like this, three-dimensional. And so if you can find a function that will model the contour of a three-dimensional figure, then you can place that function on an axis and rotate the axis, sort of like a spindle would make a baluster, or something like that. A lathe would make a baluster, I mean. So this down here is exactly the same as this up here, and this axis of revolution goes right through the center. We can find the volume of this shape. So let's say this is from 0 to 2. So what you do is you think of this volume as disks that are accumulating. Like, here's a disk, and here's a disk, and here's a disk, and here's a disk. There's a whole bunch of these disks here. Matter of fact, there's infinitely many of them between 0 and 2. If you have infinitely many of those disks, then each disk will be razor thin. And so you can just add up all of the areas of all of those disks, which are pi r squared, another pi r squared, and that would just go on forever and ever. Well, remember, just like when you're finding the area under a curve, finding the volume of this three-dimensional solid, you just integrate across your interval, and the formula for one of those disks is pi r squared. This is the radius, pi r squared. So the deal is, this pi r squared is the area of one disk, and you let those areas accumulate from 0 to 2. So all these disks just keep stacking up all the way across here until you get to the end. Now, here's the trick. How do you find this radius, which is from here to here? Or when you're down here at the bottom, from here to here? Or when you're out here, you're basically going from the axis of revolution to the function. You're getting this length right here. So this length is x squared. It's the value of the function. Similarly here and similarly here. See, right here the length is 4, 2 squared. Right here, if this was at like 1.5, then the length would be 1.5 times 1.5, which is 9/4, or 2 1/4. So the radius is x squared. So pi times the radius all squared dx. And then you just integrate like normal. So this would be x to the 4th dx, which is pi times 1/5 x to the 5th, evaluated from 0 to 2, which will give you pi over 5 times 2 to the 5th, which is 32, minus 0, which is 32 pi over 5. And this would be cubic whatever units you have, because this is volume. So it boils down to this. You just need to add up a whole bunch of disks, pi r squared, from your start to your end. And you just do that with an integral. The hardest part is finding the length of the radius, which in most cases is not that bad, but in some cases it is. So the next example I'm going to do is when the radius is a little bit harder to see. So let's say this is my function, x squared plus 2. So take your regular parabola, shift up 2 units, and let's say your axis of revolution is not the x-axis anymore, but now it's some other horizontal line. So we're still going to rotate this shape. So now we're going to get some figure that would look like this. So maybe part of a horn. you know, maybe the horn would keep coming down right here, but the biggest part, maybe the bell part or whatever you want to call that. But this shape's kind of strange, but the process is still the same. You get your pi times your integral from 0 to 4, because we're going from 0, 1, 2, 3, 4 and stopping right here. Now remember, we're going to add up a whole bunch of disks, which is pi r squared. And so the length of the radius, which is from here to the function. Well, if we were going from the x-axis to the function, the length from here to here is always x squared plus 2, but we're not coming from here, we're going from this line, which is already 1 unit up. So this length is only x squared plus 1. So that's kind of strange to see, but that's how that works. You just count from your axis of revolution straight up to the edge. So since this is 1 unit and this is x squared plus 2 units from here to here, then this part right here must just be x squared plus 1 unit. See, x squared plus 1 plus another 1 gives me x squared plus 2. Okay, now integrating this means I got to FOIL that first. So this would be x squared plus, x to the 4th plus 2x squared plus 1, which is 1/5 x to the 5th plus 2/3 x cubed plus x from 0 to 4, which is whatever you get when you plug in a 4 here, here, and here. Multiply all that by pi. Subtract off, plug in a 0 here, here, and here, multiply all that by pi. So, but the hardest part is setting this problem up, and that's how you set this problem up. So, these all form solid figures. Sometimes you have a solid figure with a hole through the center, so most of it's solid, but the middle's hollow, and that's what the next video is going to be about, and that'll be the last video for the year.